Well, here's another kind of question that we'd be interested in. What value of k, what k index, corresponds to a given omega naught? So we need to be able to kind of understand the frequency axes, and there's this correspondence between k index, omega naught, frequency in hertz, radian frequency in radians per second. So in this case, we just want to relate the value of k to a given omega naught. K naught is omega naught over delta omega, which is omega naught over, and delta omega is the distance between frequency samples for the DFT. Which is equal to omega naught over 2 pi times n. And we should say approximate, and I'll explain this in a second. Okay, so for example, well, I'm going to run a MATLAB demo here in a minute. Suppose omega naught was 5 pi over 11, which is 1.43 radians. And suppose n was 20. Okay, then k, the index of the DFT that corresponds to that, is 5 pi over 11 times 20 over 2 pi, which is equal to 100 over 22, which is equal to 4.54. Now that's not an integer, so we're going to see that that's sort of problematic. In other words, the peak value of the spectrum is not going to show up at one of the sample locations for the DFT. Okay, so here's a MATLAB demonstration, and what I'm going to do is plot a cosine that has this frequency, 5 pi over 11, n equals 20, so it's the case I just talked about. N is going to go 0 to n minus 1. Omega is 2 pi n over big N, so that's the radian frequency corresponding to those values. And here's where we generate the cosine wave. And let me just select all of these, and then we're going to go down. Okay, so try that again. We're going to select all these, and here you see we're going to take the fast Fourier transform. I'm going to plot the fast Fourier transform, and then we'll see what we get. So let me hit the F9 key, and I have to adjust it so it gets into the window here. Okay, and this is the fast Fourier transform, and we've got 20 frequency samples, and we see that there's a peak. It looks like there's a peak around about 5, okay, but we can't really tell. I can use the zoom tool to try to get in a little bit closer, and that shows one at 5 and one at 4. Well, that's not the answer that we wanted. We wanted 4.54. Well, now I'm going to plot it again. Here's the next part of this M file. I'm going to make a second figure, but I'm going to oops, I wish that thing would stop that. I'm going to plot this using zero padding, and you can see that we're going to zero pad out to 128. And now I'm going to actually plot the original values from the non-zero padded. They're going to be plotted with dots. There's the there's the dots, and then and we're going to plot that against the zero padded version. So let me select that, and I'm going to hit F9, and I'll drag this thing into our view window here. And now what you can see is the zero padded version. Now this should be remarkable and amazing to everybody who looks at it. The DFT or FFT without zero padding gives us these sampled. These show up as dots. But when we zero pad, remember there's no new information, but it does an optimal type of interpolation. And look at here, it interpolates a nice sync function, which is exactly what we're expecting now. Let me use the zoom tool to go in and see what we get. And now you see, oh, and this is in terms of frequency in radians per second. And the frequency appears to be at 1.43 or something like that. Okay, and if we go back to the original thing, 1.43 is exactly the right frequency. So without zero padding, we could not have figured that out, even though it didn't provide more information, but it did the interpolation for us. So I hope everybody got that. Zero padding gives us no better resolution. This is actually part of the last homework. No new information. But it does give us, allows us to see things like this. It interpolates. So we can interpret the spectrum much better. The other thing I want to point out is, and I'll ask you this on a test, and you better know the answer. I mean, this is stuff you really got to know. There's a peak here and a peak there. Are there two sinusoids present in the data? There's a line here at omega equals, looks like 1.4, whatever that was, and another line here at omega equals omega equals 4.9, for example. And the answer is, of course not. This is an image. This thing to the right is above the folding frequency. There's pi, folding frequency. Everything above the principal range from 0 out to pi, everything above that is an image. Okay, so that is not a real, that is not part of the original signal. That's one of the infinite number of images that are showing up because we've sampled the data.